With so many sorting algorithms out there, merge sort is extremely versatile and reliable sorting algorithm. Implementing and understanding merge sort is extremely easy. In this course, we are going to cover each and everything that you should know to implement merge sort and understand its in and out. Before we get started, I want you to introduce you to Great Learning Academy, a free initiative by Great Learning. You can access over 200 plus courses with 1000 plus hours of free content on trending high demand domains absolutely free. Register now to complete the course and get your free certificate of completion. Check out the link in the description of the video below. What is merge sort? If we talk about merge sort, let's try to understand first sorting. So sorting is a mechanism of giving order to your values, right? So let's suppose you have some values, random values, 10, 30, and then you have 5, 2, 1, and so on, right? You have these values, and now you want to maintain some order. So in order to visualize this data, let's suppose you want to see the ascending order of it or the descending order of it. That is what you mean by sorting. So let's suppose you have a class, and in that class you have several roll numbers, and some of the roll numbers are not present, and then you want to sort those roll numbers in terms of ascending or descending order. That is when you require sorting. So this is the basic intuition behind sorting, trying to give order to some kind of values or some kind of a data set, right? So in this particular tutorial, we are going to talk about merge sort. So merge sort is a classical sorting algorithm. In this sorting, every time your problem is divided into sub problems so that your problem set is reduced, and then you will be focusing on that sub problem. Similarly, every time when you're dividing your sub problems, you will keep on dividing it unless and until there is only one element left, right? If you compare it with simpler sorting algorithms like bubble is there, insertion is there, selection is there, quick is there, when you talk about its time complexity as compared to these algorithms, this is very much efficient. Now, it follows a paradigm of divide and conquer. What does this mean? This means that first you keep on dividing your sub problems, and then you will conquer those problems, and then you will combine those things. Okay. So herein we will see when you are trying to divide your sub problems, and then when you have your problem set and those problem sets are conquered, that means those problems are further, when you talk about in this example, those sub problems are sorted in this case, and then you have conquered them, and then you will combine them. That is your merge phase, wherein you will be combining your problem again, and then for forming again a single sub problem. So every time you will be dividing that sub problem, you will be conquering it and combining it. So this is how this divide and conquer paradigm works. So basically, when you're dealing with merge sort, you are focusing on two functions, that is your merge function and your merge sort function. So now let's talk about this divide. That means you're dividing your sub problems, which continues unless and until there is only one element left, because one element in itself is sorted, right? Now this is your divide phase. What about conquer? Basically, you are conquering those individual sets and then merging those two sub problems into a single problem. And finally, you will be doing it on each step, and finally you have your original array, which is sorted. Now let's talk about merge sort algorithm. So first let's talk about merge sort method. So in this method, what we are doing, we are dividing our array into further sub arrays. How we are going to do that? We are basically, if we have this array, right? And this array, let's suppose this contains 8 elements, right? This is our array. And let's suppose this is our left pointer and this is our right pointer. And now what we are doing, we are dividing it. So we need some kind of in iterator wherein we will store the sum of, and we try to calculate the mid value. How would you do it? In simple words, we calculate left plus right divided by 2. That's it, right? So we have this division, and then we will divide this part because we are calling this function again, right, on the left hand side. So this is going to call on this side. That is, we will be talking about now only 3 elements. So this is let's suppose, or let's take 4 elements on this side and 4 elements on this side. So our mid will be 3.5. So we'll be talking about elements from 0 to 3. So we will be talking about 4 elements, and then further these 2 steps are remain. Why? Because we are implementing this in recursive fashion. So now let's suppose this is our first function call, and you have these 3 steps. Let's name it 1, 2, and 3. Okay. So in the first function call, 1, 2, and 3. So this is the first function call, and in this we'll calling again. This is the second function call, and we are calling again these 2 remaining, right? And we are calling again 1, 2, and 3. Right? So in this case, again, we are calling it on these 4 elements, and it will be divided into further 2 elements, 0 and 1. Right? And in this case, again, this will be called on these 2 elements, right? Here we are talking about only 2 elements. So this is the third function call. And again, we will be dividing it. These 2 and 3 steps are still remaining. So in the fourth step, what we are dealing with only single element, right? And in this case, we are talking about only this element, right? And further, we will not be able to divide it. And in that case, our left will be greater than or equal to right. And in this case, it will be equal to. So we will return. So now it will be returned, right? And then whatever was the left over, right? Now we talk about this single element, the other element that was left behind. We'll talk about that. So again, that will be divided into 1, right? And again, this second option, I'll just erase it because it looks a little bit messy. So now what happens? Let me just put it again in red. So here we call this 4th time, and this time it returned, right? So in this case, now we will be on the second step. Now again, it will be called on that single element, and again, left will be greater than or equal to. In this case, it will be equal to, and then we return. So again, we are returning. So we have these 2 elements, 1 and 1. That means not 1 and 1 element, but there is only a single element in both these arrays, right? Why I'm saying that in these 2 arrays, we will check when we talk about merge. Okay, we'll see how that is implemented. Okay, so now these 2 function calls are done, and then we deal with merge. Now before going into the merge, let me show you a demonstration of how things look. So you have these elements, and here you have how many elements? You have 5 elements, right? And now you're dividing it into 3 and 2. Now this is your first step. The second step will be this. So now will you go ahead and create this as your third step? That means you will move on to this? No, because we saw unless and until there is no left, right? We will not go to the right. So this is your second step. Then this will be your third step. This will be your fourth step. Now you will move on to your fifth step, right? And now once you don't have anything on the left, nothing on the right, then what happens? Will this be your sixth step? No, your sixth step will be merge. So let's move on to merge now. So in the merge function, if you see, the algorithm for that is simple, that you create 2 sub-arrays. That is, one is your left array and another is your right sub-array. Now in this, you have obviously in the last case, if you have seen, we have a single element here and a single element here. Now once we have deduced out the length of these arrays, what should be the length of these sub-arrays, and we have declared the length or declared these arrays, and then we have initialized these arrays. Once these 3 steps are done, then what we are going to do, we are going to create 3 iterators, I, j, and k, and those iterators deal with, I iterator will deal with the left array, j iterator deal with right array, and k with the original array, which helps us to insert the elements. So once we have everything in place, what we are going to do, the next step is comparing the values, right? If this element, that is the element in left array, is less than the element in the right array, we are going to insert that in the original array. So now let's suppose you have 10 here and 23 here. So 10 is less than, so we are going to insert this, and we increment the k pointer. And now also our I pointer will be incremented. Earlier it was 0 and it will go to 1, right? And now what happens? Now our I is pointing to 1 and our length is also 1. So now that in that case, when one of the array is exhausted, the next array, whichever is left, right? It can be either the left array or the right array. those elements will be directly inserted in the original array, because we know for the fact that both of these left as well as right arrays will be sorted in itself. Okay, so let's see what is the next step in the demonstration. So here we had our steps, right? And this will be the sixth step wherein we are going to merge this thing. Now, will this be your seventh step? No, your seventh step will not be this. Your seventh step will be here. This will be your seventh step. Now, sixth step is done. Now you will be dividing it and you will be creating all those arrays. Now, once you have your right array, and there is no right because this left is already done. And now you had your right left. Now this is also done. Now your eighth step will be this, that you will be merging it. This will be your eighth step. Then you will be merging it. Now, will this be your ninth step? No. You have your this array, that is your left array, in place. But what about the right array? Is this in place? No, it is not. So now let's try to calculate that. Now, what will be your ninth step? This left is done. This is your ninth step. Then what will be your 10th step? This is your 10th step. Well, now there is no left, right? Now we'll move on to this right. So this is your 11th step, because this is the right side of it, right? And now when you don't have anything on the right, now you will be merging these two steps, and this will be your 12th step, which is over here. So this is your 12th step. That means you will be merging these two, and the final sorted array is this array, and you will get this array in the 12th step. So you see 10, 11, 16, 20 and 30. Now if you observe carefully, you have these individual arrays 1 and 1. So now while you are merging them, you are also sorting them. So the left array is sorted, and same thing happens on the right hand side as well. If you see 3 and 4, these two elements are sorted in this left array. So this is the reason in the right array, right? Not the left array. So now when you are merging them, you will get again an array which is sorted in itself. You see 10, 16 and 23. So if one of the array is exhausted, the next array elements can be directly inserted in your original array. Let me erase this. And you see you have your left array which is sorted, and then you are merging it with the right array which is also sorted. Now if one of the arrays is exhausted, the next array, either it can be left array or the right array, the elements from that array can be directly inserted in the original array, because we know the elements itself in either of the arrays, either the left or the right, are sorted. Okay, so this is how you execute your merge function. Now let's look at merge sort implementation. Now we know that we need to implement two methods, right? First is the merge sort method, and the second is the merge method. So first let's look how to implement this merge sort. So basically this method will take three arguments: the array, the starting point and the ending point. That is your starting index, that is 0. And if you have an array in which you have 8 elements, that means you have 7 indexes, right? So this will be 7. Okay, now we will only run this sorting merge sort function when our start is less than what? Right, or the end. That is, start is less than right, because we know only then we will be dividing it into further segments. That is, first it will be 8 elements, then we'll be dealing with only 4, then we'll be dealing with only 2 elements. That this means this, you have 4 here, you were having 8 here, then we'll be dealing with 2, then finally we'll be dealing with 1 elements, and that's it, right? So this function will be called again and again and again, unless and until you have your left less than your right. Okay, or start is less than right? Now when you have this single one elements each, the segment, and these are sorted, then you will be calling your merge function on this, and you will be sorting them in a single array. In this case it was, I guess, 10 and 23. Now it will be sorted to 10 and 23, right? So this is the how you implement your merge sort. Obviously we know that how recursion will occur, right? So let me just put the actuation record, how it looks. It will look like something this. Let's take an example here. Let's name these functions as 1, 2, and 3. So when you have your left, if you have your left, it will be called, right? This function will call this actuation record. There will be next actuation record. This will call this function, right? And these two are left behind. So again, this will be called unless and until you have your left. Now let's suppose you don't have any left, right? That means the 1 and 1 case wherein you have only single element left. In that case, it will return back. Now these statements will never be executed because you're returning it. This condition is not true, right? This condition is not true, so nothing will happen. These statements will never be executed, right? So nothing will happen and it will return back, right, to the previous statement where we call this function. So it will go on to the second. Now similarly, the second case is nothing but your right. You will be calling this on your right function. Now if that is the case, you have your right, it will call this again. It will again start the procedure of calling these 1, 2, 3 again. But if it is not the case, it will return back. And finally the merge will happen. So in this case, when we have 1 and 1, that is 10 and 23, the last two elements, then it will be called, and this statement, this step third will be executed, that is your merge will be executed. Now let's look at how you can merge these two elements. So in the merge function or in the merge method, you will have 4 arguments: the array, the left pointer, the middle index, and the right index, that is your endpoint. So in first case, wherein you have only 1 and 1 elements, that is you have single elements, that is 10 and 23. In that case, your index, obviously your lengths, you will calculate your lengths with this formula. We can calculate these lengths and it will be 1 and 1, right? And then you initialize, that is first calculating length is this, what we do here. Then the second step is initializing our arrays or declaring our arrays. Then initializing our arrays, these arrays, that means the array that we just created, 10 and 23. These are new arrays. This is your left array, ARR, and this is your right array. Okay, so you created them, you inserted the values. Here you insert your values. Insertion or initialization. Here you are just declaring it. Okay, you're just declaring it. Done. These are the first 3 steps that you need to do. So calculate length, declare your array, and initialize your array. Done. The next step is that we calculate. Let's suppose you have this case 10 and 23, right? These indexes are 0 and 0. So this is your I and this is your J. And the K pointer is nothing but used for replacing elements in our original array, which is ARR, obviously, right? And this K points to the index that is 0. The rest of the elements is whatever, we don't require them because we are just dealing with these elements and replacing them. Okay, so this K pointer points to 0 index. Now in that case, we have I, which is pointing to 0 and length is 1. Obviously it is less than. Same case will happen in here. 0 is less than L2, right? Now we compare these two values. If the element, first we will insert the lesser elements, that is 10 is less than 23. Yes, it is. So what we do, we insert this left array, whatever is the content in it, that is 10 in this, and then what we do, we increment our I. So I will be pointing now to first. Now I will be incremented to 1. Now what will happen, this I is incremented. So this block is done. This block won't be executed. Then we have finally K++. Now what happens, we increment our K because we have already inserted it in this, and now K will be pointing to 1. Okay, done. But now when we again go into this while loop, we are still in this while loop, right? Now this I is 1. So I is not less than L1 because both of them are pointing to 1, right? The I is 1 and length is also 1. So, and both these statements need to be true because we are using the AND, logical AND operator, right? So we are out of this for loop. Now what about this element, the remaining element, right? So for that, what we do, we have this and this while loop in place. So this is for the left array that we have if some of the elements are left, right? And we know for the fact that left array and right array will be sorted in itself because that's how we proceed, right? So in this case, the left array is done, but what about the right array elements? That was 23 in our case. So that will be directly inserted. You see that we have directly inserted that in our, this K pointer was pointing to here, and we have directly inserted this 23 in here. And whatever, if we have more elements, let's suppose we have 23 and 53, we know this is sorted, so we'll be directly inserting them in this and incrementing our k pointer and also the j pointer, because this j, we are only executing this because j should be less than L2. We will be comparing it with the length of with the number of elements, right? If we have two elements, we will be going from we will be traversing two times. So in this case, j was here and we had only single element, and j was equal to 0 and the length was 1. So obviously j is less than, this means that 0 is less than 1, and we inserted 23 and we incremented the k pointer. That means k is pointing here now in this location, and we incremented the k pointer and also the j pointer. So j is incremented and j will be 1, and now 1 is not less than 1, so we are out of this loop, and this will not be executed. Why? This was the reason why we were out of this initial while loop, because 1 is not less than 1, right? So this is how you insert rest of the elements that are left behind. And this does not happen only in this case, this will happen in each and every case wherein your left array or your right array have elements which are not compared, that will be directly inserted in your array, original array. Okay, now let's try to implement this. Whatever we have written, we are going to copy paste the same code in our editor. The editor that I'm going to use is Sublime Text. Now if you see, we have a class and that is named as merge sort, and in this we have merge function which takes arguments array, left and right and the mid. Okay, we calculated the lengths and then we declared the arrays, then we initialize these arrays with the help of these two for loops. Then we have these pointers which will help us to insert the values, right? And then we inserted the values if we are comparing and both of the arrays, that is the left array and the right array, have elements in them. Once we don't have elements, then we will check if there are any elements in the left array and if there are any elements in the right array. Once we are done with that, we have our array and which is sorted, right? We merge them, those two arrays, left array and sub array, we merge them. And this is how you implement your merge sort function. In this we have three arguments, start and right, and obviously start should not be greater than or equal to right, and in that case we will be returning right. And if you have seen this is how we calculate mid, right? And then we call this on the left part and on the right part, and then we merge them. This is your merge sort, right? And then we have this display function wherein we are just iterating through the array and printing out the elements. You have your main function over here, and in this we are using a static array. Then we created an object, this merge sort ob. This is your object, merge sort of class merge sort, and we have first displayed the original array, that is unsorted array. And then what we did, we called merge sort function with the set of arguments, and then we printed out the array because we are changing in the original array. So we are displaying the array that was there with the sorted elements, right? So now let's save this file and let's try to run this. Open up your command prompt and just type in, obviously you should be in the same drive wherein you have stored it, right? So we write javac and the name of the file, that is merge sort.java. We compiled it, and then what we did, we ran it. The command for that is java merge sort. So you see, you have your original array as 6, 5, 12, 10, 9, 1, and then you sorted it out, and the sorted array is 1, 5, 6, 9, 10, and 12. So this is how you implement merge sort. So we have seen all the functions plus the driver function as well as the display function. Now let's try to analyze merge sort. First, we are going to cover number of comparisons. Then, is it stable or unstable algorithm? Then we are going to cover, is it in place or out place algorithm? So now let's try to understand how many comparisons are required when we are dealing with merge sort. So let's take an example. Let's first talk about worst case and then we'll talk about best case. Space complexity, we always talk about worst case. That is big O notation. It can be n, it can be anything, right? So we always talk about big O notations. So let me clear it out and let's talk about this thing. So for worst case, let's take an example. Let's suppose we have This is the second last step wherein we try to merge these two and we merge them in a single array, right? This is about merging, where comparisons happen and then we merge them in a single array. So let's take the second last step. In that, let's do 1, 2, 3, then 4, then 5, then 6, then 7, then 8. So this is the second last step wherein we have these two partitions and we are trying to merge them in a single array. So let's see how many comparisons are required in this step. Okay, so 1 will be compared with 2. So here you have it, 1 comparison, and we'll merge them into a single array. Now this is gone. Now still 2 and 3 are remaining. So now what we do, we compare 3 and 2. So 2 is smaller and it will go in this array. This is also gone. So 3 and 4, 3 is smaller. Now we move on to 5. So 5 is gone. 5 and 6 will be compared. 5 and 4 first will be compared. We have 4, then 5 and 6, we have 5, then we have 5 and 6 and 7, we go 6, then 7 and 8, we have 7. So after this 8 will go directly in this, because we know if one of these arrays, that is your left array and right array, if one of them is exhausted, right, the next element will go directly in the merged array. So this is your sorted array, and the number of steps or comparisons required is 1, 2, 3, 4, 5, 6 and 7. That is n minus 1. Okay, now if we would have the best case scenario wherein this array is sorted, right, 1, 2, in this manner, 1, 2, 3, 4, and then 5, 6, 7 and 8. In this case, this would have been compared, this would have been compared, this would have been compared, and we have this 1, 2, 3 in this array, and rest of the elements would have been directly inserted, 5, 6, 7 and 8. Okay, let me just write it somewhere else, as this might not be visible to you guys. So just a minute. So what would have happened, so we have this array at the end, we have 1, 2, 3, and then rest of the elements 5, 6, 7 and 8 would have been inserted directly. So the number of compares would have been n by 2, that is 4, right? Only 4 comparisons. But this is the best case, and we never talk about best case. So now let's try to erase everything, and now let's see. So we have 7 steps, right? Now this we came how would we evaluated this? By n minus 1. Now what about these two cases? So we have this, first we talk about this array wherein we have 4 elements on this side and 4 elements on this side. But how would we have evaluated this array? We would have something like this, 2 comparisons, these 2 sub arrays. This is the left and the right, and then this would have been merged into this, and there would have been another 2 sub arrays that would have been merged to this, right? So how many comparisons would require to get this merged array? So now let's look at that. Let me erase everything. Now let's talk about these 2 partitions first, right? So now we merge this into that, getting those 4 elements, right? And getting these 4 elements. So now it seems that we could have compared this and then this, and rest 1 element would have been directly. So 3 comparisons here, and we have similar case here. So 3 plus 3, 6 comparisons. Now if we evaluate this and put it in a form, in the form of formula, it would have been n by 2 minus 1 into 2. Why this 2? Because same thing happens over here. Okay, so we are just doubling it out. So let me put it for in this case we have n equal to 8, and 8 divided by 2 minus 1 into 2. So this is nothing but 4. 4 minus 1 is 3. 3 into 2 is 6. So 6 comparisons, right? So this is the formula. But what happens when we talk about this? How we evaluated? How would we have evaluated this case? Now let's talk about that. We erase this thing. So in that case, we would have something like this, right? So we would have this 2, and this would have merged into this. And similarly, this would have happened 4 times, right? three more times, that is 4 times we would have such scenario. So here the comparisons would have been only one comparison, right? So in that case it would have been something like 2 n divided by 2 raised power, uh, let me put an arbitrary value like or let me put a value for in this case, then we will evaluate a formula. So minus 1 divided by 2 raised power 2 into 2 raised power 2, right? So in this case, how many comparisons we would have? N equal to 8, and this is 2 raised power 2, which is 4, which would have resulted in 2. 2 minus 1 is nothing but 1, and multiplied by 4. So 4 comparisons. Make sense? This is one comparison, and this would have directly inserted in, we would have directly inserted in this merged array. So only one comparison is required. Similarly, we have other 3 situations, that is total number of situations. Such situations are 4. So in the first iteration, when we talk about these 8 elements, when n is 8, we had 7 comparisons, then we had 6 comparisons, and then we had 4 comparisons. So total of 17 comparisons. So now let's try to evaluate a formula so that we will get this 17 as it is for the number of comparisons. So if we talk about this thing, we would have something like this. N, if we evaluate the formula, we have n divided by 2 raised power I minus 1, then minus 1, and then into 2 raised power I minus 1. Now what is this I? This is nothing but your number of levels, okay? And this level is nothing, how many times you are going to get that comparison situation. In this case, when n was what? N was 8, we had 3 levels, right? So it would have been something log n to the base 2. Now this would have been only 3, but the last merge is also there, so plus 1, okay? And this is only for the case when n is even. What about odd cases? So we take the seal of this, that is, we take the larger side. So this is the number of levels, that these I. What about this? This is nothing but your comparisons. Your comparisons, how many comparisons you are taking, and this is nothing but your nodes. So if we try to evaluate this thing, this turns out to be what? N, the seal value of log 2 to the base n minus 2 raised power log n to the base 2 plus 1. Now we need to find out that if this 17, if this equation holds, right? So in this case, n was 8, right? And the seal value of log 2 to the base 8 is nothing but 3, right? 2 to the base log 2 to the base 8 plus 1. So now if you evaluate this, this will be 8 into 3 minus 2 raised power 3 plus 1. So this turns out to be 17. So our equation holds, and the formula for calculating number of comparisons is nothing but n. Then you have your seal value of log n to the base 2, right? This is a seal value because we are taking into consideration both even and as well as odd cases. Then minus 2 raised power log n to the base 2 plus 1. What about unstable or stable? Merge sort is a stable algorithm. What does that mean? It means if you have an array wherein you have 1, then you have 3, then you have 2, then you have 4, then you have 2 dash. Now these two, this 2 and this 2 is repeated, right? Now in the sorted array, this order will be maintained. That is what is known as stability. So you have in your sorted array 1, 2, and then you have 2 dash. That means this 2 and this 2, the order will be maintained in the sorted array as well. So it is stable. And what about in place or out of place? So in place means that you are not using any extra memory, but in our merge sort, as we had already seen, that we were using 2 arrays, that is the left array and the right array, for storing, which also helps us in comparing the values and then inserting them in the original array. So we are creating extra memory, right? So in that case, this is an out place algorithm. All right. So this is the whole analysis of merge sort algorithm. Now let's talk about time and space complexity of merge sort. So first we are going to talk about time complexity. So as you can see that every time we are dividing our problem, or if you have 8 elements, we are dividing our array into further subproblems. That is, we are dividing it, right? So if we are talking about 8 elements in the first array, then we are talking about 4 elements, then we are dividing into 2 elements, then we are dividing into single element. So every time our problem is reduced by half. So when this is the case wherein you have n, then you will talk about n by 2 elements, then you will talk about n by 4 elements, then you will talk about n by 8 elements, and so on, right? If this is the case, this is the case where you are dealing with log to the base 2 and n. Why this is the case? Let me take an example. So let's suppose your n is 8 in this case, right? Log to the base 2 and value of n is 8. So this is 3. That means you will be dividing your problem 3 times. That is the correct scenario that follows in here. So you have 8 elements, then you are dividing it into 4. Then you are dividing into 2. Then you are dividing into 1. That's it, right? So you have three such instances in this example that you are dividing your problem 3 times into half. So this is the case where your complexity is log n. So to the base 2, obviously, right? So this is the scenario, but this is a scenario only for the first phase when you are dividing it. But then you are also merging it. That is the second phase. In that phase, you are doing it for all the n operations or all the n elements or iterations. And in that case, you are dealing with all the n elements. So the total time complexity is n into log n. So this is the time complexity of a worst case. And obviously this will be the time complexity for best case, because in best case, only the comparisons, as we already seen, only the comparisons will reduce and rest will remain same, because you're again checking for all the n elements, right? So in that case also, your time complexity will be n log n. And for all the time complexities, that is best case, worst case, and average case, the time complexity of merge sort will be n into log n. Log n, because of the reason we are dividing it, and then we are dividing it again and again and again. So this is a case where log to the base 2 comes into picture, and we are doing it for all the n elements. That is in the second phase where we are merging it. So that is your n. So the total time complexity is n into log n. Now, what about the space complexity? If you talk about space complexity, here we are using an extra memory, right? And every time we are using, let's suppose in the last case, we are using memory of size 1. And in the above case, before that, we are using memory of size 2, then 4, then 8. So in the worst case, when we are talking about space required, is that we are using n amount of memory, right? So all the n elements are stored, because in the last step we are using an auxiliary memory wherein we are storing all the 8 elements. So in that case, what we are doing, we are copying our elements in an auxiliary memory wherein at worst case the space that we require is n, that is the number of elements. In this case, we require 8 memory spaces, right? And so the space complexity of merge sort is big O of n, because we are using extra memory, that left and right arrays that we created. And in the worst case, we will be requiring to store elements which is equal to the number of elements. Now let's try to compare quick sort with merge sort. So we know that in merge sort, every time we are reducing our problem into half, right? So we have first 4 elements, then we have 2, then we have 1, then we merge them. So every time we are splitting our array. That will not be the case in quick sort. In quick sort, we have one pivot element wherein that element is the element wherein the right, if we talk about the elements on the right side of the pivot and on the left side of the pivot, will be elements either smaller or either greater than. So we have that pivot element as the separator between the elements that are greater than and the elements that are less than. And the pivot will have its original position in the array every time, right? That is how quicksort operates. Now, if we talk about worst case scenario, we have already studied that in worst case time complexity, the time required by merge sort is n log n, which is not the case in quicksort. It will be n square. Now, merge obviously takes n amount of, or if you talk about big O notation, it takes order n space complexity. If you talk about consistency in terms of the size of the elements, it does not depend on whether your data sets are large or small. That means number of items. Wherein it will, if you talk about quick sort, it is faster than other sorting algorithms for small data sets like selection sort. In selection sort, if the data set is small, it will take a huge amount of time, not huge, but comparatively, quick sort will be faster than selection sort in that case. If we talk about using extra memory or using the array that is there and inserting values in that same array, that is not the case in merge sort. We are using extra memory, that is, this is an outplace algorithm, and in this case it is an in-place algorithm because we are not using any extra space. If we talk about stability, quick merge sort is much more stable in terms of, if we have 2 and 2, this 2 will always be in front of this 2. That is what is stability. That means if you have some order at the time of insertion, that order will be maintained, which is not the case in quick sort. So this is the comparison between quick and merge sort. Now let's try to see one of the examples, which is one of the most commonly asked question on merge sort. So you have been given these two sorted arrays, right? And you have to merge them in a single sorted array. So if you see the input that is given to you, this is your one array, let's name it ARR1, and this is your ARR2. So if you see, this is 1, 5, 8, 10, 20, that is, it is sorted. And similarly, 4, 6, 9, 15, this is also sorted. Now you have to merge them together and the resulting array should also be sorted. So this is your problem. So how can you solve this? So what we are going to do, we are going to create a class and name it merge. And in this, we have one method which takes in arguments, that is your first array, ARR1, ARR2, and then the size of these arrays, that is n and m, which is nothing but size of ARR1 and size of ARR2 respectively. And now we will be creating another array, that is A and S, that is your answer array, and we have its size as n plus m. And we will be having our 3 iterators which will help us to insert value in this A and S answer array, right? So what we are going to do, we have this while loop which will iterate. We know I is from 0, I is 0, and it should be less than n, that is the size of this ARR1. And also we have this j pointer which is equal to 0, and it should be less than m, which is size of this ARR2, right? So these are the sizes, okay? So now whenever we are comparing, now we have these two arrays in place. Let's suppose you have 1, 5 and 6, and you have here 4, 5, 3, obviously it is sorted, 5, 8 and 9, right? Now we will be comparing these two elements, and if now we will be comparing these two elements 1 and 5. So 1 is less than 5, so we will be inserting it in the answer array, and we have our k pointer which is pointing to 0th index, and we will be inserting this 1 over here and incrementing this k to here, right? And similarly we'll be traversing. So we talk right now, our I is less, so we'll increment our pointer and it will be pointing to this location now, or this element in this case, which is 5. So now if you have same situation, right, that means I and j are same, in that case else part will be executed, and we will be pointing up, our pointer will point to the next location in this array, that is your array 2. So j will be pointing here, and we'll be pointing now to 8, and 5 will be inserted. Now what happens after that, we'll be pointing here, because we are talking about this array, right? As soon as when we have an array which is having 3 elements, let's suppose this is having 3 elements, and we have exhausted it, and in this we have, let's suppose we have 10 elements. Now we only exhausted 3 or 2 in this array. So rest of the array elements, either it can be the left array, that is ARR1, or the right array, that is ARR2. If either of these are having elements which are not traversed, so we know for the fact that both of these arrays are sorted, so we will be inserting values directly in the answer array with the help of these two while loops. So this while loop is for left side, or ARR1, and this is for right side, that is ARR2. Okay, so we'll be directly inserting the elements in this array, and after that we will be returning this array. So if you see, the return type of this merge is an array, so we'll be returning this array. So this is your merge function. Now, what about the other functions? We have display function over here, which is used to display elements. That is, we will be traversing through the array and displaying elements one by one. This is your driver function. This is your driver function, wherein you are just declaring and initializing your arrays. This is your one array, this is your two array, and then you're calling this merge function directly, because we are using here, we have this static function over here, so we don't need to create objects. So we are directly calling merge, and we are passing array and the length of these two arrays, and then finally we are displaying the answer array, which is there because we are returning something from this function and we are storing in this array, and then finally we are printing out all the elements that are sorted in our answer array. So this is your driver function. Now let's try to implement it. So now you have your class over here, that is merge, and in this you have your static function, that is merge, and in this you have these four arguments, array 1, array 2, and the sizes. So you initialized your answer array, you declared your and initialized your pointers. This is a while loop that will take care of comparison, and once one of these arrays is exhausted, then these while loops, this while loop and this while loop, take care of the rest of the elements, and then you return the answer array. You have this static function over here, that is display function. Another, you have your driver method over here, in which you are just initializing and declaring two arrays and calling the merge function and calling the display function. Now let's save this file and let's name this file as, just a minute. So the name, let's save this file and let's save it on the desktop and name this file as merge.java, right? And now let's open up our command prompt, and in this command prompt let's type in javac merge.java to compile our program, and then write java merge to run our program. So you see, we have our sorted array, that is 1, 4, 5, 6, 8, 9, 10, 15, 20, 40, 55, and 92. And all the elements are sorted. So we have used a smaller implementation of merge function, which was there in merge sort, and we have solved this question. So there can be many questions based on merge sort. You need to check out and solve them with the help of this merge sort algorithm. So this is how you implement your merge function. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell, so that you don't miss out on any new updates on video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on this video any queries or suggestions, and I will respond to your comments.